we're going to continue on with 9.6 with more, well, I'm going to go back to mathematical induction on this problem. And what you'll notice is we have these combination problems. So as a reminder, when you see these parentheses without a fraction, it's the same thing as the combination of r minus 1. So, by the way, you don't need to know that this is called Pascal's identity. It's named after Blaise, I think I'm pronouncing that right, Pascal, who came up with this. So what he realized is that you can add combinations together and it'll equal the next, sort of like the next term combination with that same r value. And this works for any value. So using Pascal's identity, what I can do is I can prove that the sum of, I guess, I hesitate to say rho because you haven't learned Pascal's triangle yet. So if you get bored before the next use, there's a triangle. It's called Pascal's triangle, which we're going to do in the next section if you've looked ahead. And that's what I mean by a rho in Pascal's triangle always equals 2 to the n power, which is pretty interesting. Now notice that it's starting at n equals 0, so my base case in mathematical induction is actually n equals 0. So if I were to try this, I can plug in 0 for n, and remember that this is the same thing as 0c0, which means that we're doing 0 factorial over technically 2 0 factorials, but all of those are equal to 1. Well, if I go to this side and I do 2 to the 0 power, that equals 1 as well. So again, I like to write out the sentence, since 1 equals 1, the base case is true. So moving forward to the inductive step, this is where we need Pascal's identity. Because what we need to do is we need to do the same thing, prove that it's true for n equals k plus 1. So I need to replace all of these n's with k plus 1. So what we have is k plus 1, 0, plus k plus 1, 1, plus k plus 2, 2, dot, 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 plus, I'm going to do not just, well, I guess I could do k plus 1, k. That's what I normally do, is like the previous term and then the next term. I don't know if that's really going to make a difference for you. Oops, definitely do not want a fraction in there. K plus 1. And what I want to show, let me do this in a different, want to show that that equals 2 to the k plus 1 power. And we know that this equation works as long as all of these are just k's. So right now I can't use this yet. And that's where the Pascal's identity comes in handy. Now I can't do anything with this k plus 1 or 0, but we've done problems like this, and why I already know that that equals 1. Because remember, it's k plus 1 divided by k plus 1. Now what I need to do is the Pascal's identity and rewrite this term using Pascal's identity, which is changing the k plus 1 to k's right here, and then what I'll end up with is k and another k. And what, if you look back at that identity, the r is still the same for this one, so the 1 that's right here is still a 1 here, but right here is 1 minus 1, so it becomes 0, 0, 1. And then same thing goes with this one. We end up with k and another k, and a 1 here, and then a 2 here. And that pattern is going to continue all the way until I get to this value, So like I'll write out k minus 1 plus k. And then this last piece that I have right here is equal to 1 as well. Same reason as this one. If I had k plus 1 factorial over 0 factorial, k plus 1 factorial, everything cancels out and I'm left with 1. So what we've established from this pattern is inside of all of those things that I rewrote. Let me find a different color. I'll use orange. Is we have this statement embedded inside of this. So what I'm talking about is we have this piece. Let's see, we have this piece. Maybe I shouldn't start with that one. Yeah, I'll go ahead and just start with that one. That's fine. I would have another k over 3. I would have all of them. Maybe I shouldn't have done that. Maybe I'll start with these ones. Because remember, k0 is the same thing as that one. That's equal to 1. k1, k2, so on and so forth until I get to this piece. So what I have there is a 2 to the k power. And then what I have is all of these are still plus in here. And I have the same thing for all of these other ones. I know I'm missing some pieces in here, but like this would be the previous term, and then this would be the last term. So I would have another 2 to the k power. So how many of those 2 to the k powers do I have? I'll switch back to this purpley color because I'm almost done. I have 2 of these 2 to the k power. Well, now that I'm multiplying with the same base, I can add the exponents, and we are done. So I want you to realize that there's a lot of cool things to be shown and proven using mathematical induction, which is why I want to have one mathematical induction on your test. I want you guys to at least have exposure to it before you go on to college or calculus or whatever you decide to do. And I also found these problems that I think are fun as well. And it's all about understanding permutation. So maybe I'll even switch back to black just to show you. And it's all about understanding, well, I don't think it's as bad as what some people think. Because remember, NP3 is the same thing as n factorial over, you subtract the 2 pieces factorial. And same thing with the right side. This is the same thing as n plus 2 factorial over subtracting the numbers, n plus 2 minus 4 factorial. Now it might make sense to you to simplify a little bit. And there's a reason why there's a 14 here, but I don't want to get too much into that. Is right here, this is the same thing as n minus 2 factorial. So remember, all of these factorials, they mean n times subtracting a number times subtracting another number, so n minus 2, times subtracting another number. Now I'm going to stop right here because now I can cancel out the n minus 3 factorial with the n minus 3 factorial that's on the bottom. And when I look at the right side, I can really do the same thing. Now, as a reminder, you're subtracting 1 from that value, so it would be like n plus 2 times n plus 1, because it's n plus 2 minus 1, times n minus 1, times n minus 2. I'm getting into the space over here, but I'm stopping there because in the denominator, that one's also n minus 2 factorial. Yeah, so those pieces will cancel. So what I would do next, which is what I would do, is I would start dividing things to the right side, I think I would do. There's a faster way, but right now I'm drawing a blank on which way would be faster. Maybe all I would do is divide both sides by n and n minus 1, which is acceptable as long as you're doing the same thing to both sides. So what I see now is on the right side, I have 14n minus 28 when I distribute. And on the right side, I have n squared, let's see, it'd be 2n plus 1n is 3n. 2 times 1 is 2. And now I have a quadratic. And we know how to solve quadratics. We've been practicing that for years. Subtract 14n over, add 28 over. We know factors of 30 that will add to give me negative 11. I believe it's negative 6 and negative 5. So that means our answers for n will be 6 and 5. Because remember, and maybe I'll just show the step. It's n minus 6, n minus 5. And the zero product property would tell us that the solutions are positive 5 and positive 6. Now, as I was making your answer keys to your homework, I noticed a sort of a shortcut. So if you want to pause the video and get your work copied down, is you can actually plug these into your graphing calculator in y equals. The only thing is it doesn't graph. So math, probability, NPR, I forgot what it was. I'm going to use XP3. And the other one was n plus 2p4. Except I'm using x instead of n. And instead of going to the graph, I'm going to go to the table by hitting second graph. And what I'm looking for is when they are equal to each other. And for some reason, it's giving me that they equal to each other at 0 and 1, which I was not ready for. The reason why 0 and 1 should not work is because the first number needs to be bigger or equal to the second number. So I'm not sure why they're telling me that 0 and 1 are equal to each other. They shouldn't be. But you can see now that 5 gives me the same y value and 6 gives me the same y value. So those are the two answers I want. I wish I had a better answer for why these answers are showing up. They should say error, but there might be some programming issues with the calculator. So 5 and 6 were the correct answers. And that's just to check your work. I expect to see this work when you get to it on the test. So I'm going to quickly do this last one because I'm running out of time. N factorial over n minus 5 factorial is equal to 18 times n minus 2 factorial. And I bet you could do this in your head. N minus 2 minus 4 would be n minus 5 factorial. Now, I will point out some shortcuts, and I do this at times, is I will cross multiply first. So I might rewrite that n factorial, because it would take me a while before I got to n minus 5. So I might stop at n minus 2 factorial, because if I cross multiplied, I could have moved that n minus 2 factorial over here. Let's see, I did something wrong. This should have been n minus 6. That's what I did wrong. N minus 2 minus 4 is n minus 6. There we go. So the 18 is still there on the right side. I have n minus 5. I'm going to leave that alone, because in the bottom I have n minus 6. Nope, I can't leave this one alone. I wish I had a little bit more room, because I need to do n minus 5 and then n minus 6 to cancel out there. I know I'm skipping that step because I'm running very low on time. So on the left side I have n squared minus n. On the right side I have 18n minus, I believe 8 times 5 is 40, so that should be 90 if you do that math. So then from here we have a quadratic, n squared minus 17n, what's that, plus 90. Let's see, factors of 90 wouldn't be 9 and 10. Or it would, because I didn't do that right. You gotta subtract 18 over to get negative. So yeah, negative 9, negative 10. So the answers on this one should be positive 9 and positive 10. Now just as a heads up, when you get to the homework, you might get some extraneous solutions because they have to work in the context of the problem. And for your homework, I'm only asking you to do number 4.